Hi everyone, let's go ahead and jump into this problem. It's a multivariable calculus problem where we have a vector valued function that represents a curve in 3 dimensions. I have a video where we find the length of the curve from t equals 0 to t equals 1, and then I sketch the curve roughly. But here, let's go ahead and find the unit tangent and unit normal vectors. So I think I'll just, without explanation, give roughly what this curve looks like. And then, don't want to drag the video on that too long, but I think it's important for us to have some sense of what we mean by the unit tangent vectors. So we have this curve on a little small piece looks something like what I'm drawing here. And no, actually, no, that's not quite right. It looks more like this. Sorry. Okay, it's from another video that you can check out that I have when I find the arc length. It's problem number 3. So if you were just looking at one point, the tangent vector at one point, unit tangent vector would be like this. And the normal vector is orthogonal to that. It's perpendicular. I said tangent, I wrote n. And orthogonal to that is the unit normal vector. That was just, I did that at one point there. Okay, so it's going to look something like that. Okay, so we're going to find those. And I have the formulas given right over here. And again, how do I know the curve is like this? I showed it something like this. I showed it in another video, a different video, which is problem number 3. Okay, so what I need to do is find r prime and then multiply by its magnitude to find the unit tangent vector. So r prime is just found by taking the derivative of each of these component functions. So the derivative of t is 1. So this is not maybe that clear, but this is square root of 2 times t. It's not, the t does not lie under the radical. And the derivative of e to the t is e to the t. The derivative of e to the negative t is negative e to the negative t. And now I find the magnitude, and that is where things start getting a little bit more involved, to say the least. Okay. So this gives square root of 2 plus e to the 2t plus e to the negative 2t. And where'd the negative go? Well, negative squared makes positive. And so how do you raise a power? You multiply the 2 times t. Now, this is not that clear, but what we have actually is e to the t squared. That's the e to the 2t part. We have e to the negative t squared. The middle term is 2, and the way you could think of this is e to the 1 times e to the negative 1. No, sorry, I don't want 1, I want t. At least the same thing. I mean, what I wrote down was true, but it didn't quite make sense for this. Okay. And so that it looks like I just pulled out of thin air. So I maybe shouldn't have done that, but I just wanted to show you, or that's one way to look at it. But this has a perfect square, so we can at least think this is e to the t plus e to the negative t quantity squared. And what you do is you multiply this out and make sure you get this up here. So e to the t squared, I have that term. E to the negative t squared, I have that term. What about the middle term? It's 2 times this product. 2 times e to t, e to the negative t simplifies to this. So the whole thing, when I take the square root of something squared, is the absolute value of e to the t plus e to the negative t. But because all that's non-negative, I just get e to the t plus e to the negative t. So that is a magnitude of r prime. And so then the vector function, the unit vector function t is r prime divided by, okay, we get r prime divided by magnitude r prime. And so this is equal to 1 over e to the t plus e to the negative t. That is this part here, that's 1 over the magnitude, times r prime, and r prime is rad 2, e to the t negative e to the negative t. Okay, it might not really seem like I had done this, but actually I was sort of worked out this problem beforehand. And in such a way that I thought it would, I don't know. So I worked out this problem beforehand, and so I'm going to do something that don't seem entirely obvious, but they make it possibly easier to differentiate. So I got one answer here. That what I need to do next is I need to find the unit normal vector, which actually ends up being the sort of the bear here, the really difficult one in some ways. Well, for some people think it might be easy. For me, I thought it was a little bit of a challenge to do that. So actually, I'm going to multiply this through. So maybe I shouldn't have yellowed this. I'm going to simplify it in a certain way. That might look sort of weird, but okay. So here's my simplification, which someone might say, hey, that doesn't seem simplified. But anyway, I am taking this and I am going to multiply the numerator and denominator by e to the t for all of these. To write it in a different form, which is, it just possibly is easier when I find the derivative, and especially will match the answer in the back of the book. So that's part of why I did it that way. But I think it's a little easier to take the derivative later on. And so the thing is, e to the t times e to the t makes e to the 2t. And then e to the negative t times e to the t makes e to the 0, which is 1. So then over here we have e to the t times e to the t. That's e to the 2t. Again, e to the t times e to the t is e to the 2t. E to the negative t times e to the t is 1. The thing is, when I do all this, I start thinking, well, the whole time I thought, is there a super cool trick to make this look better? This, when I multiply e to the negative t times e to the t, I get e to the 0 is 1. Not to look better, but actually easier to find the derivative. So actually, I think in the back of the book, this is the way they express t, the unit tangent. Okay, so now I'm going to find n, which unit normal vector, which is t prime divided by its magnitude. So taking the derivative of t actually isn't even that easy, but then finding the magnitude of that involves a few little tricks. And so, all right. In order to do this, we just have to jump in and just bite the bullet. We're going to use the quotient rule here for these. So this is going to be radical 2. The derivative of radical 2 e to the t is radical 2 e to the t. Then we multiply by the denominator. Subtract, leave this same numerator. And then we multiply by the derivative of the denominator. The derivative of the denominator is 2 e to the 2t. And then we have the denominator squared. So, really, it's too much. But not for some people. Okay. I mean, it's pretty fun, actually. It's sort of the point of view. Again, the quotient rule, take the derivative of the numerator, multiply by the denominator. I mean, if you think of this as just a really fun puzzle, then it's not that bad. You can think of life that way. All the hassles and everything, it's just a really cool puzzle to solve. Okay, so I did that one, quotient rule, and then we'll do this one. You can do quotient rule, but yeah, maybe I will. Okay, so it's not really the easiest way to do the quotient rule, but I guess I will since I'm on that rule. The derivative of the numerator is 0. Typically, I wouldn't recommend using always a quotient rule because in fact, it looks stupid if I do that. This is the same thing as negative e to the 2t plus 1 to the minus 1 power. So use the chain rule there. But you could use the quotient rule. So the derivative is going to be negative of negative 1 e to the 2t plus 1 to the minus 2. So I'm using the chain rule here, and then you take the derivative of what's inside, and that's 2e to the 2t. So what a lot of stuff here. All right, and then I have to sort of make sure I didn't make a mistake. But anyway, so distributed property goes square root of 2 e to the 3t plus square root of 2 e to the t minus square root of 2 e to the 3t. So always satisfying to cancel things out. That's always so fun. Those two cancel. Divide by e to the 2t plus 1 squared, comma. Similar deal here. We're going to get 2e to the 3t plus 2e to the 2t minus 2e to the 3t. Those cancel. E to the 2t plus 1 squared. And then comma, it's sort of unfortunate, I have to go to the next line. 2e to the 2t over e to the 2t plus 1 squared. You know, it would be really even better is if I could fit this in all on one line. Okay, so this gives us apparently, oh my gosh. Okay, this gives us some good stuff. Hold on, I made a mistake here. This is not canceling. The second one is, but I dropped a 2. So that's not all good, but I don't want to start a new video anyway. So I dropped the 2 there. See, there's this 2 right here. It's 2 times radical t. This is a 2 there. And then this, there's a little canceling. I mean, I just simplify this, but this is going to give radical 2 e to the t minus radical 2 e to the 3t. So I had worked out this problem, so I looked it up what I was doing, and I realized I made that little mistake right there. So so this has a 2. And, okay, comma. 2e to the 2t over e to the 2t plus 1 squared. 2e to the 2t over e to the 2t plus 1 squared. The thing is that these two are the same, which indicates that these are equal to each other plus a constant, and it's true. If you take this one and add 1, you can work it out, then you'll get this. Because they both have the same derivative, so that means they have to differ by a constant. So this term I'm circling minus the other actually equals 1. So, all right, that's true. Anyway, then there's a trick that I am going to do, which is I'm going to factor out the denominator. That doesn't seem all that tricky. Seems okay. But I'm also going to factor out square root of 2, and I'm going to subtract out, ready, e to the 2t. So taking out the square root of 2 right here leaves no square root of 2, but if I take out e to the 2t, it leaves e to the minus t. Again, I factor out radical 2, and taking out e to the 2t gives e to the t. This one, taking out radical 2, leaves radical 2 behind. Taking out e to the 2t just leaves 1. And then over here, taking out e to the 2t makes 1, but then there's radical 2. Okay, that makes this vector part look easier, and then I have this up. Now, the thing is that when I find the magnitude, which I do need to do, when you find the magnitude, any scalars pop out. I mean, you can just factor out the scalar, but you have to take the absolute value, but this is all positive. So that is why I did that. I factored out the term first so that it would be easier to do this other part of the magnitude formula where I square things. So if I didn't take that out, it would be very messy inside this squaring piece of the radical. Okay, square root of 2 e to the 2t, e to the 2t plus 1 squared. Oh my gosh. Now I expand this. E to the negative t squared is e to the negative 2t. I multiply minus 2 e to the negative t, e to the t, plus e to the t squared, which makes e to the 2t. Square root of 2t is 2. Square root of 2, okay, so I have 2. Does this make you want to major in math? Isn't this so much fun? Look at this, I made another mistake. E to the 2t plus 1 squared. All right. This is e to the negative 2t, and this piece here, e to the negative t times e to the t, simplifies to 1. So it's minus 2 plus e to the 2t plus 4. Plot thickens. Square root of 2, e to the 2t. E to the 2t plus 1 squared, square root of e to the negative 2t, negative 2 plus positive 4, that makes 2, I can do that, plus e to the 2t, and this is a perfect square. This is going to become e to the minus t plus e to the t squared, and we can work it out. It's a little bit like you guess it, because you see those two perfect squares, and then when you, e to the negative t squared and e to the t squared. You see those, and then you think, hold on, is this going to be the square of a binomial? And sure enough, gosh darn it, it is. Okay, so that is square root of a positive expression squared is, well, let's square root the square, and we get e to the negative t plus e to the t. So, you can do the absolute value because that's what you're supposed to do, the square root of something squared. But because they're positive, you don't have to do that. Okay, now this gives even further simplifying. If oh my gosh, I'm about to overdo it, my brain. Okay, e to the t multiplied by e to the negative t plus e to the t. Why did I do that? Because I want some cancellation here between those two, which we'll see we get. So I multiply that, and I get square root of 2, e to the t. E to the t times e to the negative t is 1. E to the t times e to the t is e to the 2t. And so cool that there is simplifying cancellation between those two terms. So this therefore gives square root of 2 e to the t divided by e to the 2t plus 1. What? Wasn't that just an amazing amount of stuff there? Okay, then we're back to n, which is t prime divided by magnitude of t. We have all the ingredients. Let's go for it. Let's cook with it. So here is, this finally is the magnitude of t prime. I think. I better check my work. Yes. And so when I divide by it, I'm going to multiply by the reciprocal. So I have e to the 2t plus 1 divided by square root of 2 e to the t. Then I multiply by t prime, that vector, which is that giant bunch of stuff up there, which I could just, I suppose, just copy and paste. Not everybody has that option, unless they're using an iPad also. But anyway, copy, or even duplicate. Duplicate, maybe shrink it a little bit. Okay. Let's put parentheses around this part here. And then we see there's cancellation with this and this. A lot of cancellation, actually. So square root of 2 and square root of 2 cancel. So this gives, and also e to the 2t divided by e to the t just makes e to the t. So we get e to the t divided by e to the 2t plus 1. Then e to the negative t minus e to the t, radical 2, and to make it even better, I multiply the e to the t through, Keep in mind, e to the t times e to the negative t is 1. E to the t times e to the t is e to the 2t. So this gives 1 minus e to the 2t and radical 2 e to the t, radical 2 e to the t. Everything's fine, except I'm sort of forgot the way the book wrote it. I should have looked at that earlier. Did they bring the other part inside or not? Leave that outside or put it inside. I have the solution right in front of me. That is the way the book writes the answer. Okay. So I got that one. So that's, that's something to be proud of. Okay, we have that. Now, that's only part A, but it's the end. The unit normal vector was challenging. Now, for the next part, B, find the curvature. This symbol for curvature sort of looks like a K, but I'm pretty sure that's a kappa. And the thing is, there's a formula that I'm actually, let me just copy down and paste the formula I have above here. Okay. So, okay. The formula that I have been using a lot of is that the curvature kappa is this part right here. That is very convenient. If I were starting this problem from scratch, I would use this formula. However, if I had not already found the unit normal, the unit tangent vector, I would just use this formula. But since we already found t, the unit tangent vector and its derivative, I'm going to use this one because it's like we already have all that work. But otherwise, if I were starting from the beginning, I would use that one. Okay, so kappa equals magnitude of t prime over magnitude of r prime. And I already have this magnitude of t prime. That was super fun. And I have magnitude of r prime somewhere. That was this part. So I already have those. But by the way, if you didn't have those, I think that what happened there? Oh, there we go. Okay. If you didn't have these pieces, I think that this way is actually not even that difficult to do. I mean, I worked it out that way. It's fine. It's not even close to the amount of work there was to find this thing. Okay. So here we go. Then kappa is equal to the reciprocal of magnitude of r prime. So that's 1 over e to the t plus e to the negative t times the magnitude of t prime, which is square root of 2 e to the t. Let's put parentheses around that. And then this is e to the 2t plus 1. And once again, it looks like maybe this seems like, I don't know, something weird or doesn't simplify, but it does. Okay, so why is that? Let's duplicate this and write it down again. Because of this piece right here, if I multiply the top by e to the t and the bottom by e to the t, we'll see something. This becomes e to the t. Okay. Distributed property gives e to the 2t plus e to the t times e to the negative t is 1. And then we have radical 2 e to the t, e to the 2t plus 1. So this gives, oh, brother, am I doing it right? Yes. Okay, square root of 2 e to the 2t, e to the 2t plus 1 squared. I mean, but I think using this is not bad either. All right, so anyway, there we go. So that gives that answer, that finalized everything, this super long video. Okay. Well, like I said, I would think this is too hard to put on a test problem. It's a bunch of algebra. If you can do this algebra, think you can maybe even do anything. I mean, that was a lot of algebra. All right, okay, that's all. Bye.